Hi. Let's talk about friction. Friction is exactly what you think it would be. It's a resistive force between two surfaces in contact. So suppose I have some sort of crate here sitting on, say, a metal floor, and I try and push that crate with some pushing force. There'll be a frictional force that resists it. And actually we know from experience a little bit about this. If I push a little bit, the crate doesn't move, apparently the frictional force just equals the pushing force, otherwise it'd be moving. If I push harder, the crate still doesn't move, apparently the frictional force got bigger. So if we were to make a graph of the frictional force versus how hard I push, we would see until the object moves, these are just equal. If I push a little bit, friction pushes back a little bit. It's pretty clever. Push harder, friction pushes back harder. Push harder still, the friction resists even harder. Up to some point, have you ever noticed when you push something, when it just starts to move, it always gives kind of a little jerk, it kind of breaks free and then starts moving? That's because the force to get something moving and the force to keep it moving are different. Those frictional forces are different. There's some maximum frictional force, F max, that's bigger than the force of friction after an object's moving. So after the object is moving, this force drops to some force we call Fk. Now experimentally, and from experience, we know some things about what this depends on. We know the force depends on how heavy this is, or more specifically, it actually depends on the normal force, because it's not just how heavy, but if we were to lift up on the object a little bit, we get less friction. And lifting up actually decreases the normal force. So it also depends on the surfaces in contact. So if they're pushing this on a metal floor versus ice versus wood versus carpet, we get different answers. So the surfaces matter. And all of that is encapsulated in a couple of formulas. We need one formula for maximum and one formula for after it's moving. So F max is just some constant mu sub s, that's the Greek letter mu, looks kind of like a U, but it's Greek letter mu, times the normal force. This is called the coefficient of static friction. And this just tells you how big the friction could possibly be. Where this mu is measured from experiment, and it just depends on the surfaces. Is it wood on wood, metal on ice, etc.? You have to look that up in a table or measure it. So that's the coefficient of static friction, and N is the normal force. The bigger the normal force, then the more friction you've got. Now, mu K is mu kinetic. Static means something that's just sitting there. Kinetic is something in motion. F kinetic is just mu K, coefficient of kinetic friction times N. So this is the coefficient of kinetic friction. And this just tells you how much friction you've got after the object's in motion. And once it's in motion, that friction settles down to a pretty much constant value, no matter how hard you push. It won't be completely constant, because as the object gets faster and faster, it might heat up and that friction could change. These are actually approximate equations, but they're good approximations. Now, so for example, let's look at this case of just a crate, a wooden crate sitting on metal. For a wooden crate on metal, mu sub s is approximately 0.5, and mu sub k is approximately 0.3. Those are just numbers from experiment. So if this is a 12 kilogram crate, for example, and if we're pushing with horizontal forces, we can know roughly what the friction will be. If we push with a force that's not horizontal, if this is a little harder, we'll see that shortly because it changes the normal force. So in this example, I'd say I need to know the normal force for either of these. There's a normal force up, there's an mg down, N is just mg in this case because there's no other vertical forces. That's just 12 kilograms times 9.8 meters per second squared. So that's 12, 9.8 times, that's 117.6 newtons. So the maximum frictional force I could get is now mu S in is 0.5 times 117.6 newtons. It's just half that, or 58.8 newtons. That's the most frictional force this crate could resist with. Any more push than that and it's going to break free and you'll be able to push it along. Now, what if it's already in motion? How much frictional force could I get? Then you would need to use not mu static, but mu kinetic. All that changes now is mu kinetic. So if in motion, so already in motion, now friction kinetic is mu kinetic in, and that's just 0.3 times this normal force of 117.6 newtons. 117.6 is 35.3. So it's smaller. So once it's moving, there's less friction, which again agrees with your everyday experience. So let me do just a couple more examples with you, and then you can practice it in your homework as always. So let's calculate an acceleration when we just have a horizontal force, and then we'll do a slightly more complicated case where you have a force at an angle. So here I've got a crate on a floor. It's again a 12 kilogram crate. And I'm going to apply just an F equals 120 Newton force. It's horizontal. There'll be a frictional force. And I'm just going to say mu sub k is given is 0.25. And I'm going to give you that the object's already in motion. And I'll say, what is A? All right. We always have to find all the forces. So there's an mg down. There's a normal force up. We know in the x direction, F equals ma. So we've got an F net, the total F. So F minus little f equals ma. So A is big F minus little f over m. So I need little f. This is F kinetic because the object is already in motion. So F kinetic is mu kinetic in. So I need n. N minus mg in the vertical direction is 0. So in this case, n is just mg. It's 12 kilograms times 9.8 meters per second squared. That's the weight in this case. But normal force does not always equal weight. It just does in this example. So that's 117.6 again. So there's the normal force. That means the frictional force now is 0.25 times that. That's 29.4 newtons. And now I have what I need to find the acceleration. It's 120 newtons of pushing force minus 29.4 newtons of friction over 12 kilograms. And that gives me an acceleration of 7.55 meters per second squared. So there's one example. Notice how we made progress. In any problems before now, you had to just be told the friction force. It was 2 or 12 or 15 or something. Now we've learned more. Now we've learned how to determine the friction force if we know something about the surfaces. Wood on wood, steel on ice, rubber of a car tile on pavement. We can look up those in tables, engineering tables, those mu's. It could be like bone on the kneecap bone on with synovial fluid on another bone. Now, let's do another example. This will be our last one. So now I've got my crate again. It's still 12 kilograms. There's still a frictional force and it's still in motion. And now I'm going to apply my force at an angle. So it's 30-degree angle. This is still 120 Newton force. And again, I want to find the acceleration. All right, let's find all of our forces. There's a normal force up. There's an mg down. Applied this force like pulling on a cable. And there's a frictional force. And we have to determine the frictional force. And these are the same surfaces, so mu k is 0.25. In the x direction, what forces do I have? Well, I've got an F cosine 30 here. So F cosine 30 minus the frictional force is max, where A is F cosine 30 minus F over m, but I need F. Fk is mu kn, but I need n. Now, to get n, it's a little more complicated. It's not equal to mg, because I've got this other vertical force. I've got this F sine 30 here. So now in the vertical direction, I've got n plus F sine 30. That points up, minus mg is 0. So n is mg minus F sine 30. So n is 12 kilograms, 9.8 meters per second squared, minus 120 newtons, sine 30. I just, to save time, I didn't write all those units in. So n there is 57.6 newtons. Now that I know n, uk is 0.25 times 57.6 newtons. That's 14.4 newtons. Now that I know Fk, I can put it in over here, and I've got 120 newtons cosine 30 minus 14.4 newtons over 12 kilograms. And my acceleration is now 7.46 meters per second squared. So there you have it. So once again, just to rehash, I wanted an acceleration. Sum of the forces in the x direction equals ma. One of those forces was friction. To get friction, I had to do our new equation, mu n. But to get n, I had to find the normal force. So I had to use my understanding from previous of how to find normal force. That's why we learned how to do it. It wasn't just an exercise. Now that I know how to find the normal force, I can backtrack, get the frictional force, plug the frictional force in, and get the acceleration. There you have it. So again, of course, you'll practice it in your homework and in your in class. See you soon.